Welcome back to the channel. Today we're diving into the 5 core fundamentals of mechanical engineering that every student, designer, and engineer must understand. Whether you're working on product design, CAD modeling, or real-world manufacturing, these fundamentals shape everything we build. So let's jump right into it. 1. Material selection and its properties. Every design starts with one crucial decision: which material should I use? Material selection defines the product's strength, cost, durability, weight, and manufacturability. When selecting a material, we must look at its key properties. Strength, ability to withstand load hardness, resistance to wear or abrasion ductility, how much it can deform before failure density, impacts weight thermal and electrical properties, important for heat-sensitive designs, corrosion resistance, crucial for outdoor or chemical environments. The material you choose must align with the function, cost, and safety requirements of the product. That's why tools like material charts, Ashby plots, and design standards are used in engineering decisions. 2. Stress analysis and load distribution. Once the material is selected, the next question is, can the part survive the load? Stress analysis helps us understand how a component behaves under tensile load, compressive load, shear bending torsion. We calculate stress equals force divided by area, but in real-world conditions, things get complex. Loads may vary, distribute unevenly, or cause fatigue failure over time. That's why engineers use tools like free body diagrams, factor of safety, finite element analysis, FEA. Understanding stress paths and load distribution helps prevent failures, cracks, or deformation, ensuring safety and reliability. 3. Kinematics and Dynamics. Mechanical design isn't just about strength, it's also about motion. Kinematics deals with how things move. Dynamics deals with why things move. Key points include velocity and acceleration of mechanisms, linkages and joints, gear trains, cams and followers' mass, inertia, and energy transfer. Whenever you design a mechanism, like a robotic arm, slider crank, engine piston, or gear system, you must understand how the parts move, how forces act on them, and how energy flows. This ensures smooth movement, reduced vibration, and optimized performance. 4. Tolerance and fits. In engineering drawings, dimensions alone are not enough. You need tolerances to specify how much variation is acceptable in manufacturing. Why? Because no machine produces parts with perfect size. There will always be a slight deviation. Fits define how two parts come together. Clearance fit, loose, easy movement, transition fit, intermediate interference fit, tight, press fit, proper tolerancing prevents, loose parts, misalignment, jamming, assembly failure, costly rework. Standard systems like ISO and ANSI help engineers define tolerances clearly and consistently. 5. Manufacturability and assembly, DFMA. At the final stage, we ensure the design is easy to manufacture and easy to assemble. This is where DFMA, Design for Manufacturing and Assembly, comes in. Key principles include reducing total number of parts, using standard components, simplifying geometry, avoiding hard-to-machine features, choosing manufacturing processes wisely, milling, turning, injection molding, casting, 3D printing, etc. Designing for quick assembly with fewer tools. Good DFMA reduces cost, improves product quality, and speeds up production. In short, a great design isn't just strong, it's easy to build.